Okay, let's start. Um, so you can also follow on Zoom. I should pin video. Okay, topic for today is class NP. So in this lecture, I will say the definition, give examples, an equivalent definition using non-deterministic machines, which explain the name NP, then inclusions, done polynomial count reduction, NP-hard, NP-complete. So that's for today. Okay, so why do we care about NP-completeness? So it is when you're doing research, so you need to solve problem for client or whatever. And so if you know that problem is NP-hard, then, well, your boss wants program that always runs on all instances, runs in like a fraction of second, and gives correct answer. And so in theory, this corresponds to the class P. So if your problem is in P, then you have a chance to achieve this. But if your problem is NP complete, then there is no chance to achieve this for normal human mortal. So if you know about NP completeness, you can recognize this, that this is such a problem. So Bals gives you a problem. You can recognize this issue and tell him immediately that you will fail to give a program that always replies in seconds and is provably correct. Yeah.
What the boss gives us an X-complete problem? Do we just quit from the job? Or?
Well, X-complete implies NP-hard, so you can tell him it's NP-hard. I will fail for efficient program.
Okay.
Yeah, so even there exist stronger things like exponential time hypothesis, which says that 3-SAT cannot be solved in time better than 2 to the power n, if n is number of variables up to polynomial. And so it means if your problem is NP complete with some reasonable reduction, it's really no hope to solve all instances exactly. Okay, but this is again philosophy. That's why you need, but by the way, in research also, like you try to make a plan, like, oh, I start with this problem, then go to this problem. There is a long chain. And so how do you know when you're building this chain, you go in the right direction? Well, if you go from P to NP problem, NP complete problem, you go in the wrong direction with high probability. But that requires you to recognize, oh, this problem is NP complete. And so now I do project with company, and it's each time, no, not each time, but let's say more than half of meetings, this comes up like, oh no, we cannot do it like this because this problem is NP. Can we drop this assumption from the model? It's too complicated. We need to drop things. And if you drop something, it becomes NP complete. Okay, but enough philosophy. Let's try to, let's go over the 5 points that we have to do. So definition of NP, class NP, so that represents problems for which you can verify. Look, we speak about decision problems. If an instance is in the class, if the answer is yes, then there is a way to verify answers efficiently in polynomial time. So class NP is the class of all problems for which membership can be checked efficiently using a certificate. Yeah, certificate. It's kind of a proof, like I will give an example. For example, let us look to a delivery guy problem. So what you get there is you get a set of a matrix with distances. So if there are n cities, you get a matrix n squared distances, all pair, okay, divided by 2 is symmetric and so on. Yeah, all distances. And the question is, can you make a circle that visit a cycle that visit every place once, and for which the total distance is below a given number? Oh, sorry, input is pairwise. Okay, let me write it.
Well, just TSP, yes.
Yeah, TSP is the same. Yeah.
Well,
traveling salesman problems.
Well, the certificate is just a chromosomal cycle, and we can check.
So a target distance.
So the certificate is like an NP problem that can be That's equally hard.
Let us say target distance D.
It's just if you ask to find the component,
Let's say Q,
it's just a set of vertices which
and then
which
D I.
of course have the edges between them, and it's just your answer, and you can check whether its answer is correct.
Ah. Yeah, okay.
Distances and question.
So NP problems is when we can check the answer in polynomial time.
There. This is cycle. So start with one, and then I1, I2, and so on. I10. So this. So now I'm writing this problem. It's a cumbersome problem, but it's very common problem for deliveries, like in a village. -1 plus B and N. 1 is smaller than target. So here is the problem. Is it readable?
It's
Can you read? I didn't hear it. What you said.
we cannot read some small letters which are above the D's.
Yeah. So there's this DI1, DI2.
Yeah, but we cannot see. We cannot these letters.
I will not use them. Don't worry. It's just because I don't know how to write it nicely. But okay, basically you can say there is a fully connected graph and every edge has a given weight. And can you have a Hamiltonian cycle for which the weight is at most a given value D, which is part of the input. So this is delivery guy problem or traveler salesman problem. It's also used in like for drilling machines. So that there is a bunch of holes that need to be drilled and the head has to go. And then you can save some percentage of money on the time that the head, like most of the time the head is going from one hole to another hole. So, okay, but actually this problem has approximation algorithm and quasi-linear time when the distances are from Euclidean distances. So if you have embedding on points in the plane, and you use Euclidean distance, then it's not so difficult problem. So you can approximate it. Okay. But what's the feature here? What is important here is that a solution can be verified efficiently. So if we get an order of the points, so these points, they're all elements of 1, 2, till n. So basically, this one. And so this is called a certificate. So if we know these points, so if the answer is yes, then we are able to verify it if we also given a proof, like if we get the order of the circle. So the question is, does there exist a cycle? But when we are given the cycle, we can check it. So we just have to check that all these numbers are different. No number is repeated. And that there are n of them in this list, and that connected, we just have all distances. So and the input is all pairwise distances. Or j from 1 to.
So there is at least an edge between every pair of.
Yeah. So a fully connected graph with n nodes, and every edge has a weight. So that's the same. Okay. So This problem is in class NP because if the answer is yes, there is a way to verify it if somebody gives us a certificate. Certificate in this case is just a list of points, and then we can do these additions, which go fast. Okay, next. Let's give a bit more examples. The K colorability. So here the problem, K colorability, input is a graph. And then the question, but K is not part of the inputs. So the problem is called K colorability, so K is fixed. And the question is, can you assign to each node one of K colors so that no edge connects two nodes with the same color? So this is, for example, radio wave station, like assignment of radio waves to radio station is this problem. Like every station has its own color, means its own frequency, and they're connected when they're too close, when they're close enough. And so no two different stations can use the same frequency if they are close.
Well, but if K equals 2, it's pretty easy question.
Yeah, exactly.
Not NP.
Yeah. Can you assign? Okay, I will not write it one of K colors.
So it's just K color.
Such that no edge connects the same nodes of the same color. And so for K equals 2, as a person has already said, this is easy to solve. Like a greedy algorithm will do it correctly. So it's possible. It was an exercise. If there is a cycle of length, you cannot do it. If there is no such cycle, then greedy algorithm will be successful. Okay, so this is, here it is easy to know the answer. For tree colorability is NP-complete. So nobody, if the graph has n nodes, nobody knows an algorithm that runs faster than exponential 2 to the power n up to a polynomial.
Well, it's just checking all possible columns, yes?
Yeah. Okay. There are some interesting algorithms, but they work on, so there is actually a related problem. So if you're promised that the graph is tree colorable, can you in polynomial time color it with a bit more colors?
Well, it's pretty easy because if we can color in K, we also can color it with a K plus 1 or plus 2.
Yeah, but you need to find it in polynomial time. So give the algorithm. So
we must use all the colors and the number of colors is
no. So the question is, I give you a tree colorable graph. Can you color it in polynomial time with 10 colors?
We don't know the coloring. Yes, we just know.
Yeah, no, we don't know the coloring. Yeah. So that's like a funny problem, and the people do a little bit better than 2 to the power n over 5. That's the number of colors they need to do it in polynomial time. So it's some funny thing. Don't remember it.
And it's and is the number of.
That's the number of colors K.
And n is number of
nodes in the graph. Yeah. And that was some curious thing. That's the best people can do.
And doesn't depends on the edges numbers. Well, K colors.
It's a worst case over all graphs. Okay, but I should not speak about this and continue with the lectures. Each time if I think about something fun, then we will never cover any material. Okay, so you see that like a small change in K dramatically changes things. There is also another question. So Hamiltonian cycle, it's a cycle that visits every node once. So you're given a graph, input a graph. Can you visit every node exactly once using a cycle? Then there is Eulerian cycle problem. You heard about this.
What?
Eulerian cycle. It is a problem. Like given a graph, can you make a walk that visits every edge exactly once? I should say Eulerian walk, but that's just a walk through the graph. Okay. Let's give an example. No,
Well, it's just, yes, it's also.
yeah, in the same way as can you draw this graph with a cycle without lifting your pen? Yeah. And so here you cannot do it. And so there is a simple trick. Just look whether all the nodes have even degree, because each time you arrive, you have also to leave.
Yeah.
And so this problem clearly is in P, because checking whether all nodes have even degree goes very fast.
Yes.
But when we care about visiting every node exactly once, it's NP hard. Best algorithm runs in time 2 to the power n times poly n. So with dynamic program, like that, for Hamiltonian cycle, the answer is also like a sequence of nodes. But actually, these problems are closely related. To prove hardness of these problems, usually people use Hamiltonian cycle. And so the number of permutations of nodes here, it is n factorial. So brute force takes time, n factorial time, which is n, basically n to the power n.
Does there exist some relaxation with the quasi-polynomial sign for Hamiltonian cycle or not?
But this is quasi-polynomial, but there's no point in quasi-polynomial because Hamiltonian cycle, there are no numbers in binary. So quasi-polynomial, you don't need to know this, but I'm just, there is a question. Quasi-polynomial means that do you have algorithm that is polynomial in the value of the numbers? So normally the numbers are given in binary. So you need an algorithm that's polynomial in the log of the value of the numbers. And quasi-polynomial, but for Hamiltonian, it's a strange question. But for traveling salesman problem, this question makes sense.
Well, yes, I know that it is.
Yeah, but okay, it depends like on the details. So if you only, the question is what do you want for the distances? But you can satisfy triangle inequality and still be strongly NP hard, it's called, like when you allow for, when you I don't remember the definition of strongly NP hard, but the answer is no. So the problem you mentioned is strong. So PSP is strongly NP hard with general distances that satisfy triangle inequality, but not in embeddings in the plane.
It's an interesting question.
Wait, I'm not sure about embeddings in the plane. So no. Well, in practice, it is polynomial time solvable because you can approximate when you get an embedding in the plane. But again, I am distracted. We should speak a bit about some examples of problems in NP, and I didn't say the formal definition yet. Okay, so let's go to formal definition. And the formal definition uses notion of verifier. So know that all our problems, we discussed it in the last lecture, they reduce to problems, we can view them as languages. So here, if we're given a bunch of numbers in Q, we can encode them in binary and speak about the decision problem in binary. Yeah, so numbers, okay, a graph is also like a graph we encode as incident adjacency matrix. So a graph with n nodes is given n squared, is size n squared in memory. This internet is not working. Yes, so for definition, we will speak about decision problem on languages. And let's go to the definition of verifier. So a verifier is a Turing machine that receives two strings as input. Polynomial time verifier is a machine that receives two strings as input and checks whether the second string is a certificate for the first string. So for example, a verifier for the Hamiltonian cycle problem is just a permutation of the nodes. And this machine might check whether indeed all subsequent nodes are connected in the graph, and if no node is repeated and the list of nodes is indeed n. Okay, so one more time, a verifier is a Turing machine that has two inputs. The first one is interpreted as a problem, the second as an instance of the problem, the second one is a proof. That is supposed to be a proof that this instance, the answer is yes for this instance.
The proof, not the solution, like
the solution. Yeah. So for example, the click problem, then the input is a graph, certificate is the click. And the verifier will then check that the second input is indeed a click. And it will answer yes or no. Yes means that he verified that the second argument is indeed a click. No, if you notice a problem. Okay, so definition, polytime verifier. Right. X and C. So it should run in time polynomial in the length of the first string, time polynomial of the problem. Time only length of X. So that's it. And then either says accept or reject. Okay. And then we say that a language belongs to NP if there exists a polytime verifier okay, language L over sigma belongs to LP if there exists a polytime verifier such that so two conditions for every X in L for every X in L there exists a certificate such that VXC accepts. And for every X in not in L, every certificate is rejected. Okay, so that is definition of class NP. So every word in the language, there should exist a proof that the verifier accepts. For every word not in the language, every proof must be rejected by the verifier. And how long can the verifier work? Well, if the verifier could run in exponential time, then a lot of then all the examples we gave would be in the class. Well, they're in NP anyway, but okay, then it would be easy. Sorry. Okay, so what I'm saying is that the verifier must run fast. It must run in time polynomial. It's a bit like Sudoku.
Well,
If you see the solution, then it's easy to verify correctness, but finding the solution might be difficult.
we interested in polynomial sum verifiers just for NP or in general?
Yeah, it's a question, like it's personal question. Are you interested?
No, I mean,
Yeah.
if we want to build some reductions in other classes, do we also need polynomial sign?
I don't think for this course we will need it. But when we study, no, we will speak about p-space. Well, there exists also like a verifier definition of next, the non-deterministic variant of X. So I will define it at the end of the lecture. So, okay, that's the definition. And so I already let us look at the click. So the input problem is a graph and a number k, and the question, do there exist a click of size k in the graph? So can we find k nodes such that every pair of nodes is connected? And so what will the verifier do? So can somebody say what might be a verifier for the, so this problem, that's a click problem, is an NP.
The input of the verifier is the graph K and
Well,
certificate. No,
Yeah.
the nodes of the click.
Yeah, V1, V2, V and then what will V do? It checks that there are at least, whether we have at least k nodes.
Yeah, and that they are click.
That they are different. Then it will check.
that
Yeah, then it will check that for every pair of nodes, they are indeed connected in graph K.
yeah.
Yeah. So that's okay. Easy definition. More examples, and so K colorability is very similar. Input is a graph. So X will be a graph here, and then the certificate is just a list of colors for all the nodes of the graph. And then the verifier will check, so K is fixed and the colorability, K colorability. A verifier will check that all colors are at most K, and then for every edge that things are different. Okay, now there is a tricky problem. It's integer programming. Integer linear programming. Okay. Let us give a problem that appears to. I will speak about it soon. Let's speak about another problem that looks like a problem in NP. So the input is a set of equalities. So Diophantine, the Diophantine problem. So input set of equalities. Equalities of natural numbers. So there is actually like a famous problem. So x to the third, y to the third, z to the third is equal to 29. Does it have a problem with x, y, z integer numbers? Is this readable? Yes. Just the marker is also bad. Okay, and so here, what do you think? Does it have a problem, a solution?
and the X, Y, and Z should be different, or
It doesn't matter, might be equal. equal. Come on, that's an easy question. Find solution for this equality.
Well, yes, is it the one and the 3?
Yeah. So 1, 1, 3 is solution. Okay, now change the question. 30. So now you cannot answer this. It's impossible because smallest number is more than 1 billion. So answer is yes, but X, Y, Z are bigger than 1 billion in absolute value. And so there is open problem. Nobody knows answer. Okay, and so in the Diophantine problem, equation problem. So you're given equality an equality. So just equation, I mean equation in many variables. Question. Does it has solution over Z? Okay. And so I claimed, and so there is famous guy, Matiashevich, who proved that this problem is undecidable. But many people think that this problem is an NP. So, but all problems in NP are decidable. Yeah, we will speak a bit about it later. And so this problem, it looks like to be an NP, but what's the problem with our verifier? The problem is, so if we have a solution, then we can check it. But the problem is that solution might be very big.
And it can be exponential in the term of our input.
Yeah. Exponential, but this one is undecidable. And so exponential is not even enough.
Yes.
It can be bigger, like if you look to the coefficients, they're given in binary, but you can have any tower of exponentials and you will find equations for which the smallest solution is even bigger. Because it encodes the halving problem. So in one equation, you can simulate somehow a Turing machine. Okay. So this was actually one of Hilbert problems in the 1900. Okay, but don't speak about this, just teach the lecture. And so there is another problem called integer linear programming. And so here the input is a matrix and a vector. Let me say m times n, or n times k, and a vector d, either of size m or k, I don't remember. Let me think, it should be of size k. And the question, so does there exist an x? Is it readable? Yes. Does there exist r, x in Z? Sorry, I'm mistaken, not rk, so integer linear programming, so everything is in Z. And can we find in zk such that, let me rewrite the question here, exists x in zk such that ax smaller than b?
Well, as far as I remember, it's simply hard because we can take mean values cover and just build a reduction between them, yes, between IOP and mean values cover, or am I mistaken? Well, just 0 and 1 will be whether if there is an edge or no, and
Yeah, so you are right. This problem is NP hard, and I will explain the reduction later in the lecture. But there is another question. How do you prove it is an NP? Because we might run in the same problem. So there might exist an X, but this X might be a very, like this contains rational numbers, and numerator and denominator might be huge integers. So for each component, so for some component, it may be a ratio between two huge numbers. And so how do we know that a simple solution exists? And I always forget to prove. So there exists some theorem about cones, and one time I proved it using some formula with determinants to get solutions of equalities. But okay, you don't need to learn about it. Just remember that integer linear programming, it belongs to NP. Okay, more examples. Okay, then we are finished with this part. So I've explained this. Now let us, so what does so NP stands for non-deterministic polynomial time. And so this name comes from another computational model. And this model is called non-deterministic Turing machines. And so what's the non-deterministic Turing machines? It's a Turing machine that has two transition tables. And so we can consider, so at every computation step, it may arbitrarily choose one of the two transition tables to continue the computation.
only two or more than one?
It doesn't matter. If there are more than one, then you can reduce it. If you say I want 3 options, then if you say I want 8 options, then you can like reduce the problem to 3 choices of between 2 options.
By you random, I decide to continue.
But it can decide in 2 ways. And now I must say what it means for a machine to accept. And it accepts an input. So in deterministic machine, it accepts an input if computation terminates in an accept state. Non-deterministic machine accepts input if there is a way to choose between the 2 tables so that the machine terminates in an accept state. So if there exists one way to choose between the tables so that the machine terminates in an accept state. So let me write this definition.
Are we going to talk about alternating to the machine or later?
Alternating Turing machine? No, I don't speak about it. You said I didn't. You asked about alternating. Yes. Yeah. No, it's advanced. Okay. So non-deterministic Turing machine. I will not write the definition. Please look in Zipser book. Most of you are at home. So I will just say that it's Turing machine with, I will just make a picture. And every computation step, like for the first step, it chooses between 2 tables, delta 1 and delta 2. And for the next step, it again chooses between 2 tables, delta 1 or delta 2, and so on. Okay, and in this way, we get a tree of possible computation. And when these computations stop, they might say accept or reject, accept, reject. I will write R for reject and A for accept. Okay, and so for every input, we get such a tree. And then the machine, we say that the non-deterministic machine accept input X if there exists at least one leaf that accepts. If all leaves say reject, then the machine rejects the NP. Okay, so that's the definition of non-deterministic machine. So the runtime of the machine is equal to the time of the longest computation path. So in other ways, the maximal depth of the tree. So the maximum, so the depth of the tree, the maximal length between the root and the leaf. Okay, it's clear what is non-deterministic machine and what it means for non-deterministic machine to decide the language. So a machine decides a language if for every string in the language there exists an accepting path in the tree. And for every string outside the language, every path rejects. Okay, and so now we can define the class and time.
Question: do we care about infinite loops in this case?
Okay, if there is an infinite loop, then for this input, we don't know whether it accepts or rejects. But now I will define, so the main definition is a class n time f of n, which I want to define here. And here we require that all computation paths run in time at most order f of n. So we say that L is in n time f of n if for every x in L, if there exists a non-deterministic Turing machine n that runs in time order f of n and decides the language L. That's what that means. For every x in L, there exists accepting computation path, and for every x not in L, every computation path is rejecting. Okay, so that's the definition of n time f of n. And so now there is a theorem that says yeah, NP is equal to the union of n time. And so what should I write here?
F to the power of C of n.
Yeah, n to the power c.
I forgot. What does the U mean?
Union.
Oh.
So this is a language n time f of n is a set of languages, or maybe class of languages. Class is used for set of sets. So it's a class of languages,
Yeah.
and then we take the union of all these classes. So for every, so it contains all that runs in linear time, quadratic time, cubic time, all the non-deterministic machine. And so here is the theorem. And there is equality. So we need to prove two inclusions. So first one, if a problem is an NP, then we can decide it on some polynomial time non-deterministic machine. So how can we prove this? Anyone has idea? So we know that, so we want to have L in NP, and we want to prove that L in n time n to the power c. So there exists.
We can brute force the solution and use the verifier to check every solution.
Okay, but how does a non-deterministic machine brute force solution? It doesn't have a loop.
Well, if we have a TSP problem, we just check all the all possible permutations of our vertices and big
Yeah,
big
that's a good
permutation.
example. Yeah, but I should have given an example of non-deterministic algorithm. So let us say a Hamiltonian cycle problem. Like given a graph, can we go through all the nodes? Can we visit all the nodes exactly once by following edges? And so what will the non-deterministic machine do? It will go to the first node and then non-deterministically guess one of its neighbors. And it will continue like this. When it sees a node it has already visited, it will stop and reject. If it sees a node that if it comes back to the first node, it will check whether it has seen n nodes. And if it indeed has seen n nodes, then it will accept. So do I need to repeat? So non-deterministic algorithm, it starts in first node number 1, then it goes to random neighbor. If this recursively, it goes to random neighbor. If this neighbor is seen already before, it rejects. Unless this is neighbor 1, and then it will check whether it will count the neighbors it has seen, and if it's seen n of them, then it will accept. And so this machine, you can view it as a tree. And all the leaves are a possible attempt to form a Hamiltonian path.
Well, okay, then if we have an NP problem, we can solve its problem with a non-deterministic Turing machine just by guessing the certificate.
Yes.
And in the other direction, we can
wait a bit. Let me repeat for everyone.
We can
So
bit by bit
yeah.
guess the certificate.
Yeah. So we have two transition tables. So we can have a transition table that say write 1, and the other says write 0, and then we loop over this state a certain number of times. So we also count the number of times, because
So
note it needs to be run in time f of n, order f of n with f of n a polynomial. So we need to count and stop after we done enough guesses. And so we can guess the certificate. And then, so we use polynomial upper bound on the length of certificate. By the way, here it says it should accept some certificate, right? But it should accept it in polynomial time. So it will read at most polynomially many bits of the certificate. Yes. So even if C is a string that's exponentially long, it doesn't matter in this model. Because the time is measured by the first argument. So if there are, so it runs in time poly in the length of x, which is, yeah, 2 strings are the input and only the polynomial in the first argument, length of first argument. Okay, so
so in one direction we just guessing the certificate, yeah. And in another direction if we can.
Sorry, you're too fast. Okay. So so non-deterministic machine will go in 2 steps. First step, it will take some space on the tape after the input and guess the certificate, and then it will return to the beginning and simulate the verifier and output the same answer. And so if x is in the language, then it means that there exists an accepting branch. So if x is in the language, it means there exists a certificate. And so the non-deterministic machine has one computation branch where it guesses the right certificate and then ends in an accept state. If x is not in the language, then regardless of the certificate it guesses, the simulation afterwards will always lead to reject. And so this is proven. Okay, and now we want to do the other direction. And you had already an idea. So let's say that L is in n time n to the power c. Then,
well, now we want to say that we have a verifier, and we need to simulate. Well, we just use an accepting branch of our non-deterministic machine, and run on such.
So what's the
accepted branch.
certificate? What here you need to build a verifier. So what will be the certificate?
It's just an accepting branch of
Yeah.
of our machine.
So a branch, there are only two options. So a branch can be written as a bit 0 go left, 1 go right. And so if the certificate will be an encoding of the branch, and the polynomial time verifier will just simulate the non-deterministic verifier, and each time it needs to choose a branch, it checks it from the certificate. And so this is the same. Okay, is this clear? It was brief explanation, but maybe it works.
It would be not bad if you would repeat this.
Repeat, yeah. You want me to repeat both of them or only the last one?
Oh, the last one.
Okay, yeah. So now we know that there exists a non-deterministic machine. So we assume there is, for our language L, there is a non-deterministic machine, and all the branches have length n to the power c. Now we need to build a verifier. A verifier gets two inputs. It will get input x. And so now, given x, we need to say what verifier x and c will do. Okay, C will be a binary string. And we will interpret C as a path in the computation tree. So to do it, we just say, like, when we go left, we write 0. When we go right, we go 1. For example, 0, 1, 1, 0 is this corresponds to this computation path in the computation tree. Okay?
Yes,
So, verifier gets an input, and then it constructs, it will start to follow the path in the computation tree using the certificate. So it simulates non-deterministic machine, and each time it needs to simulate one step, it needs to know which transition table, and it chooses it according to the certificate. Sorry, yes. Okay. So should I repeat it one more time?
oh, it's okay.
Yeah. Very good. So we have, so this is done. Now this goes very quickly, I hope. So we have the inclusion P, a subset of NP. So why is this true?
Well, because we can just
Yeah, with this definition, we can just ignore
we can just-
certificate.
yes.
If it's in P and polynomial time, we can figure out the answer. So verifier will be a machine that ignores the certificate, computes the answer, and then always accepts, or if the answer is yes, and always reject otherwise. Okay, so that's clear.
Can you repeat?
Yeah.
The,
So when a problem is in P, it means that for each x, there is algorithm that runs, or Turing machine that runs in polynomial time and tells the answer. Okay.
and we can just use that.
Yeah,
as a
we use the answer.
Yeah.
We don't need certificate at all. So this is very easy. Or for non-deterministic machine, we can make it deterministic by setting the two transition tables equal. And that's even easier way to see it. Okay, second problem, second inequality, NP is a subset of P space. So above my head. The light is a little bit, but yeah, people see it.
If we use only polynomial sign, then we can't mark more than polynomial number of cells on our table. And
No, not, yeah.
Suggestion, we can just brute force all the verifiers and they will be polynomial length.
Yeah, so that's, we just said that we can assume that C is of polynomial length because verifier runs in polynomial time. And so students say, let's just have a loop over all certificate, brute force search them. And so how much space do we need? Then we apply your technique. We know machine runs in polynomial time. So simulating V requires polynomial space. And the only thing we have to do is keep a counter over C. But the length of C is just a bit string of polynomial length.
So we're using the fact that the composition of two polynomials is polynomial.
Yeah, we just add 2 times a polynomial.
Okay, but such proof won't work if we talk about that space, yes?
Well, it will also work, but you speak about composition of polynomials for some reason. But by the way, X is closed under composition, under reduction, so it would also work.
Well,
Yeah,
well,
it would work for yeah.
It's just two exponential. Well, exponential of exponential, it's
Okay, actually, what you say is an exercise, so you can discuss it with Nikita. Okay, so what I want to say, oh, I got them here, the exercise. Okay, you're bored. Okay, so but is this inclusion clear at least? And so what's the space that we need? The space to simulate V, which is polynomial, plus a space to keep our counter over the certificate. And that's also polynomial. Polynomial plus polynomial is polynomial. Okay, so here we're done. And now let us speak for last 20 minutes about polynomial time reduction. So I will delete, I will remove everything. So 2 minutes break or 1 minute break. Okay, so to reduce one problem to another means to map one problem to another. And so in daily life, for example, we arrive in a city we don't know, we are lost, and we have a bad battery, and so we need to find our hotel. So this problem of finding our hotel reduces to finding a place to charge battery of phone, and then we can use Yandex Maps or whatever to find hotel. So you transform one problem to another, and Latin word reducer means make smaller. So the idea is that you make the problem smaller. And this is kind of misleading. But the reducer means to lead. So that's the thing you need to focus on. Education means to lead out of stupidity and helplessness.
so now we're
So conductor in an orchestra, he leads everyone through the music. They're all viaduct or whatever. Abduction is kidnapping. So to lead to it. So reducer is to lead. So reduction means to lead your problem somewhere else. Okay, and what does it mean? So example, the clique problem, or remember, and the independent set problem. So you can reduce the clique problem to the independent set problem. So remember, input is a graph and a number k, and the question exists a clique of size k.
and it will be polynomial time reduction.
Yeah, and we will speak about in the polynomial.
Because we can just invert all edges. Well,
Yeah.
if there is an edge, we say that there isn't an edge, and vice versa. And after that, we use the same algorithm.
And so the operation is easy. So how do we go from, how do we map a clique problem into the independent set? So it's, as you just, I just repeat for people in Zoom. Yeah? So we just invert all the edges. So in the graph, all edges become non-edges. Let us take. So inverse of the graph means that, there are not many edges. And this graph. right? This guy is connected to, oh, and
Diagrams.
yeah. That's, so we use operation of inversion. And so instead, or sorry, the click problem. So the input is a graph and a number k. And the reduction is that we invert the graph and we get equivalent problem. So if we can solve this problem, then we know the answer here. So there is this famous question, like on Facebook, can you find 300 people that are pairwise friends of each other? This is exactly click problem. And then here, this like machine, last lecture I spoke about it. So you have a bunch of tasks in a factory, but two tasks cannot be done simultaneously if you need the same machine for some. So for every task, you need a bunch of machines simultaneously. And so if somebody invents polynomial time or very good algorithm for this machine problem, then you can solve the Facebook problem because you invert the graph and then solve it. So that's the goal of this theoretical thinking that you're trained now, to like look from high level and see analogy between problem and then transfer ideas that some guy had for this problem and another guy had for this problem. And so that's to help you become this guy where everyone goes to if a problem is too difficult. Okay, so yes, so click problem, independent set problem. So this is an example of reduction. So what is formal definition of reduction?
So a reduction.
So language A over an alphabet sigma. That's right. F is reduction. That's our definition. Okay, the marker is that. That too. That too. Fully time reduction.
Well, we can say that there is two languages, A and Q.
Yeah. I'm not, sorry, I'm wasting time. So before you
on effects in A and no X and A, if and only if F from X on B and just F is a reduction.
yeah. So here we have sigma star, and here we have a language A. Here we have gamma star. So there is another alphabet gamma, gamma star all words of this alphabet. And we have B and a function F mapping gamma star to, sigma star to gamma star is polynomial time reduction. If every element outside A goes outside A, every element inside A goes inside B, and F can be evaluated in polynomial time. Poly time computable. That means you can compute f of x in time poly length of x. So there exists a C such that f of x can be computed in time length of x to the power c. That's really bad. Last chance. Okay, this one is a little bit better. So let me write a complete definition. That so F from sigma star to gamma star is poly time reduction from A over sigma to B over gamma if one can compute f of x in prime order length of x and to the power c. If there exists a constant c, which the one took, and x is a, even only if f of x is b. That's the full formal definition. So let us do, we finish the lecture with some examples. So there's 13 minutes, right? And then it's good timing.
In this definition found in Sipsa's book, I tried to find the by the word reduction. And
yes, polytime reduction. It should be in chapter 7. You need to look. They also have mapping reduction, but that's like without without bound on the runtime of F. They only require it's computable.
So f of x will run in time in exponential time.
No, polynomial time
Oh,
and the length of
polynomial.
x.
Length,
Yeah. So that means that if you apply a reduction, then the new string in gamma cannot be too long. Its length must be bounded by a polynomial. Otherwise, you don't have enough time to write it. Okay. And so here the clique and independent set example satisfy the condition. Okay. So here for k equals 3, the clique exists. And here the independent set exists. And vice versa. So then we say that this problem polytime reduces to this problem. And the same is true in the other direction. Okay, so let us do two more definitions. Two more reductions, maybe the one you already discussed. So from integer programming, integer linear programming to, from independent set problem to integer linear programming. Well, I will here write, recall what is integer linear programming.
Well, I started to talk about reduction from invertex cover, but I think
It's easier.
any NP-complete problem will work.
Yeah, I just, for introduction, I do the easiest one.
Okay.
So b and e to the power n, and the question exists x and the c to the power n, such that ax is smaller than b. So, and now I claim that there is a reduction from independent set. Polytime reduces to integer linear programming. Okay, so we can map this to this. And so how does it work? So let us take again an example. Let us say that this is an instance of independent set.
Well, the idea I think is the same. We just can mark 0 if there is an edge and 1 if it's not, and we just have a version of integer linear programming task, but it's just a 0, 1. I think.
Yeah. Okay. So now I need to tell you what is A and B. So we will prove that we can map this problem. So we're given a graph and a number k. And now I need to give you matrices. I have to give you A and B. And I have to say what is K and M. And so the number of variables M will be the number of nodes. Okay, that's a bit confusing. So let's change it to N. Because it's in graph theory, N usually represent numbers of nodes. Here there is a conflict with input size, but since N and N, so a graph of size N is represented as a string of size N squared. But since they're polynomially related, it's not dangerous. We don't care in this area. We don't care about polynomial. Okay, so we will say N is equal to number of vertices. And so the number of variables will be the number of vertices. And the idea is that if they are 1, they are in the independent set. If they are 0, they are not. And then for every, so how many equalities will we have? K will be equal to number of edges. So we will make an equality for every, K number of edges, we need 1 more. And so we will require that, so here for every edge, we will require that at most one of the 2 nodes is in the independent set. So here we have that x1 plus x2 should be at most 1. So now I will write down a list of inequalities. And then from this list of inequalities, we get these matrices. So in the same way, x1 plus x3 should be at most 1. And then x2 plus x3 should be at most 1. And so we continue. We get a few more. This is clear. And this number of equations we get in this way is a number of edges. And we get 1 more equality because we require that the sum of all x's is at least k, because we need k elements in the independent set. Right? So plus x6, no, 5 we have. X5 is at least k. Okay. And this is of the form that we are given. But the last inequality is greater than. So how do we solve it?
Can you repeat the question?
Okay, so here we have all inequalities. At most 1, and so on. So we know for these equalities how to build A.
Okay.
And the B's are all 1s. But for the last one, so we don't have at most. We have at least. Some should be at least k. How do we fix it? So we need to turn the inequality.
Well, just multiply on -1.
Yeah, indeed. Yeah, and just I'm checking if everyone is awake.
Am I right that the same construction can be used to prove that next problem is NP hard to, well, it's just we take or not take in the
okay, yeah, if knapsack with integer coefficient, yeah, but okay, it's easy to have for integer. Yes, you're right.
and after that you can just well, okay, relaxate them not on the integer but on arbitrary.
Yeah, but in this, so now we have proven that binary integer so okay, so now next example I will prove that the independent set reduces to well-known NP-complete problem, and then the lecture is finished. Oh, I need to quickly say what is NP-hard and NP-complete. Okay, so I will need a few. No, okay, I will say the definition and then stop. Okay, so if you believe, okay, let's now go to definition of NP-hard and NP-complete. Okay, but are we convinced that I have written down a reduction? So given a graph and a number k, you now know how to write A and B. Yeah, from the coefficient you construct A, And from these upper bounds, 1, 1, 1, 1, and minus k in the end, that's our vector b. So we have mapped from this to this, and if independent set exists, then we know there exists a solution, integer solution to the set of inequalities. Because we set xi equal to 1 if it's in the independent set and otherwise not. So we know that the solution, so the question now is it equivalent? So we have to check if the answer is yes for the first problem, the answer is yes for the second problem. And this seems to be clear. If independent set exists, we can find values for x that are either 0 or 1, so that this is satisfied. Oh, I now see that I forgot some. Okay, maybe one should also add x1 between 0 and 1. And same for x2, so that we don't have negative values and so on. So we actually have number of edges plus number of nodes, 2 times number of nodes plus 1. Okay, a little bit more. So, okay, now the other direction. In this new set of equations, so clearly if independent set exists, after this change, the forward direction still holds because we choose zeros and ones according to blah, blah, and so on. Now the other direction, if there exists a solution here, then we know all values are either 0 or 1 because we care about solutions that are integer. And then the independent set is precisely the set of nodes for which the variable is 1. And we know that no two such nodes will be connected because otherwise, for this edge, the inequality is violated. So it works in both directions. Okay. Then the last task for today. So this is done. Now I need to say what is NP-hard and NP-complete. So problem is NP-hard if every problem in the class NP reduces to this problem. Okay, sorry, I forgot to.
Every problem in a class
Sorry, I need to give you 2 properties of reductions. So first lemma. If A is in P and A polytype reduces to B, then sorry, if B is in P, then A is in P. So how do you prove this lemma?
Well, it's easy. We just run the algorithm which decides the B, and after that we use the function which reduces our problems, and polynomial from polynomial is still polynomial, and we're
Okay, so let me repeat it. So what we do, we get x, and we want to know whether it's in B. So what we do, we apply the reduction. So here we have a reduction f. Sorry, we have A and we have X and we want to know whether it's an A. So then here we have a machine that decides P and B in polynomial time. And so we will just check MF of X. And we will check if it's in B. So we just output the answer of this computation. If it's in B, then we know X is in A. And if it's not in B, we know X is outside A. Now we have to check that this machine runs in polynomial time.
B is in polynomial time, so the machine is
and we know that M runs in time, MF of X runs in time order length f of X to the power C1. But we know that f of X length of f of x is bounded by so the length of x to power c2. So order because we can evaluate having polynomial time, so its output can be at most a polynomial. And so order f of x to the power c1, this is bounded by order length of x to the power c1, c2. And that's what student means with polynomial of polynomial is polynomial. And that's why the class x is defined not with linear coefficients and exponent, but with polynomials. Yeah.
Because it's once an exponential.
Yeah, it's because they want this lemma also to be true with exponential with the class x. Okay, this lemma also holds with p replaced by NP. Oh, I shouldn't have removed the proof because it is the same. So, and this is easy, the same argument, but with non-deterministic Turing machines. Okay, and then some general property. If A polynomial time reduces to B and B poly time reduces to C, then A poly time reduces to C. Yeah, transitivity also holds with reductions. And why is this? Because
the composition of polynomials is
and polynomial of polynomials is we just have to check the run. So we apply two compositions after each other. So we go from A to B, and then imagine there is C here. But then again, the runtime can become larger for this reduction because of the size of the input becomes larger. But same argument. Okay. Yes, and after we understand this, let us say what is NP hard. So language B is NP hard if every language in C for every A in NP A poly time reduces to B. So it means that if there exists an easy way, if you have an amazing algorithm to solve B, you get an amazing algorithm to solve every problem in NP.
Okay.
So definition B is NP hard if for every problem in NP, there is a reduction from this problem to problem B. And so there are two interpretations of being NP hard. One can say that if you find an amazing algorithm to solve problem B, then if you find an amazing algorithm to solve this problem, you have an amazing algorithm for essentially all problems in A. Or you could say that's negative news. You will never find a good algorithm for B, because then you will find a good algorithm for all problems in NP. And now the last one, B is NP complete. If NP complete, if B is an NP and B is NP hard. So that's it.
Does there exist some problems that are NP hard and NP complete?
Yeah. All the problems we discussed today, click, independent set, they're all NP complete.
Okay.
What else did we? Binary integer programming and all our problems, also in industry. All problems either in P or NP complete.
Well, the whole problem is NP hard, but
Yeah, sorry, but but each time, like tactically, they want to optimize something. They don't not interested in solving the halting problem. So they have very specific goals. So it's very rare, but there exist problems that seem to be in between polynomial time and NP-complete. For example, factorization of integers, like finding prime factors. This problem is believed to be intractable, but it's also believed if it's NP-complete, it means NP equals co-NP, something that nobody believes. But it's important for secure cryptography. Another one, and I mean, if you work in a company, that one you might need is subgraph graph isomorphism is another candidate. So it's also believed to be intermediate, but they're like the only ones that can appear with some small chance.
well, Alexander Kozaczynski on seminar told us about the interesting algorithm for checking the isomorphism of graphs.
Yeah, I remember. I listened. Yeah, and then I missed the second seminar. Okay, yeah, but this is all for today. So then at 7:50 we will start seminar. Okay, bye.